Next up, we have Natilla Shanahan. She's a senior project manager with Vector Corrosion Services. And she's going to be talking about deterioration, identification, and rehabilitation of some pre-stressed concrete piles.
Good morning. Thank you for joining us here. And I'm going to start my presentation by briefly talking about the corrosion mechanism and the marine exposure environment. Then I'm going to talk about the substructure on Tunney Bridge in New Jersey and the evaluation, the corrosion evaluation that we performed. And I'm going to finish up with the cathodic protection of the substructure. So in order to have corrosion, you have to have four components. You need moisture, you need oxygen, you need a metallic path, which in reinforced concrete, that's your rebar, and you need an electrolyte. In reinforced concrete, the electrolyte is the concrete pore solution. So if we take out one of these components, we can stop the corrosion from occurring, but that's usually not possible. In the corrosion reaction, as you all know, corrosion occurs at the anode. That's where we're seeing rust buildup and rebar section loss. And at the cathode, there is no section loss and there's no corrosion. But you have to have both an anode and a cathode to have a corrosion reaction. In new concrete, reinforcement is protected by the naturally high pH of the concrete pore solution that causes formation of a passive layer on the rebar surface. However, when chlorides or CO2 penetrate from the environment to the rebar depth, they destroy the passive layer on the rebar and cause corrosion to initiate. Besides the rebar section loss, corrosion process causes a lot of damage to the concrete because corrosion products can occupy up to 7 times the volume of the original iron metal. Buildup of corrosion products causes tensile stresses in the concrete. These stresses cause cracking. The more corrosion products build up, the more stresses develop, and then cracks grow, become delaminations, and with time, delaminations become spalls. For marine structures or for marine bridges, the element that is at the most severe risk for corrosion is the substructure. The substructure can be further divided into 3 different zones. There is the submerged zone that is always below the water level, the tidal splash zone that is exposed to wave action and marine spray, and then there's the atmospheric zone that is not in direct contact with seawater. And the rest of the bridge is also in the atmospheric exposure. So out of these 3, the most severe exposure occurs in the tidal zone. This is due to the repeated cycles of wetting and drying that provide the oxygen, moisture, and high chloride exposure to the concrete. In the submerged zone, even though there is still the same level of chloride exposure, there is less oxygen, so corrosion does not occur quite as fast. And in the atmospheric zone, this is a dry environment, so corrosion rate is reduced. And also there's a reduction in the chloride exposure because it's exposed to chlorides in the atmosphere, which have to deposit on the concrete surface and then migrate to the rebar depth. This is a photo of Tunney Bridge in New Jersey, which you see on the bottom. The bridge connects Toms River to Seaside. Toms River is located on the mainland and Seaside is on the island. So this bridge is exposed to seawater. It's in the marine environment. The bridge was constructed in 1969. It's a very long bridge, just under 4,900 feet long, and has 50 spans. As you can see in the photo, there is also a notable elevation between the abutments and the middle of the bridge to allow ships to pass under it. The deck is supported by precast pre-stressed girders, which are on top of bents with precast pre-stressed cylinder piles. This bridge has 4 different types of bents that range from 3 piles all the way up to 6 piles per bent. And this is a detail from the original drawings of the piles. These piles are hollow. and have a thickness of 5 inches. The piles have 24 pre-stressing strands and a spiral reinforcement around the pile. The original drawing specified a cover depth of 1 inch and 1 3/8 inches. And as mentioned yesterday, historically, cover depths have been significantly lower than what is specified right now. And now we know that these cover depths do not provide a very good protection in corrosive environments. So a routine inspection identified the presence of widespread cracking in the piles. The crack widths ranged from hairline cracks all the way up to 1/2 inch wide cracks. So after this was identified, New Jersey DOT reached out to WSP to perform an evaluation of the piles, and WSP reached out to VCS to assist them in evaluation of the extent of corrosion and providing a corrosion mitigation solution. Due to the size of the bridge, we couldn't look at every single pile, so the structural engineer selected 24 piles for us to inspect. That had a range of different conditions from hairline cracks all the way up to 1/2 inch cracks. Our testing methodology included ground penetrating radar survey, electrical continuity testing, corrosion potential survey, chloride sampling, carbonation testing, and openings. GPR is an electromagnetic tool that is used to locate the reinforcement inside concrete and also determine the cover depth. We knew the cover depth from the structural drawings. However, we wanted to see what it actually was in the field because, as we all know, things in the field can vary. So we found that the average cover depth was very close to what was specified. It was 1.3 inches with a standard deviation of 0.2 inches. Cover depth is extremely important in determining the service life of concrete. The two equations at the bottom of the slide show the estimated time to corrosion initiation. The top equation shows the time to corrosion initiation due to chlorides, and here you see cover depth X is squared. The equation on the bottom shows time to carbonation-induced corrosion, and here again cover depth D is squared. So a reduction in cover depth will have a significant effect in reducing the service life of the structure. Electrical continuity measurements showed that approximately 50% of the strands were electrically discontinuous. We also performed corrosion potential measurements, also known as half-cell testing, to determine the probability of active corrosion in the piles. This was done to ASTM C876. In this test, a positive terminal of the voltmeter is connected to the reinforcement, and the negative terminal is connected to a copper sulfate reference electrode. The reference electrode is then placed on a grid pattern on the concrete surface, and the potential is recorded at each location. ASTM provides a table for interpreting the corrosion potential measurements. ASTM says that anything more electronegative than negative 350 millivolts is at 90% probability of active corrosion, and anything more electropositive than negative 200 millivolts is at 90% probability of passive steel. And then measurements in between are in the uncertain range. So this slide shows two typical corrosion potential survey maps that we collected. One is for the shorter pile and one is for the longer pile. So what we saw was that shorter piles had active corrosion for pretty much the entire length of the pile. And in the longer piles, corrosion extended for about 10 to 12 feet above the water surface, and the top 2 to 3 feet had passive reinforcement. This plot shows the results of chloride concentration testing. The horizontal red line is the corrosion initiation threshold of 350 parts per million by mass of concrete. The solid vertical green line is the cover depth determined by GPR, and the dashed lines are cover depth plus or minus 1 standard deviation. So as you can see, all the samples had really high chloride surface concentrations. They ranged from about 3,500 to 7,000 parts per million. And as expected, chloride concentration decreased with increasing depth. However, what's most important here is the chloride concentration at rebar depth. And for most of the samples, that was well above the corrosion initiation threshold. We also performed carbonation testing by exposing a fresh concrete surface and spraying an indicator solution. And this is the photo that you can see here. If the indicator solution turns a pink or purple color, this shows that the concrete has a high pH, and if the indicator does not change color, this is a sign that the concrete is carbonated. Now, testing for carbonation together with chlorides is important because if there is a combination of carbonation and chlorides, that can result in a more severe corrosion than either one of these causes alone. The most important test that we did, and the most important from the structural engineer's point of view, was openings. Because before the investigation, there was a question of how much section loss was in the cracked piles. We did openings in the piles with cracks that ranged from 1/8 to 1/2 inch. And what we saw that in all the openings, there was 100% section loss of the stirrups. So when I said previously that typically reinforcement corrosion will cause cracking and then cracks will develop into delaminations and spalls, this doesn't necessarily occur in marine environments when you can have water movement through cracks, either from wave action or tides. The water movement washes out the corrosion products that build up around the reinforcement, and it does not allow rust to build up enough to actually cause delaminations. So in marine structures, you can have cracking and severe section loss without any visible indications beyond the cracks themselves. I'm not sure if you can see the spiral reinforcement here. It's indicated by the red arrows, and it looked like somebody just cut through it. So for corrosion mitigation, VCS recommended installation of galvanic cathodic protection jackets. On the right side of the slide, you see a schematic drawing of the jacket. The CP jacket is an overbuild type rehabilitation that can provide cathodic protection and concrete repair essentially in one step. So in a CP jacket, we have an outside FRP jacket. Then the anodes are placed inside the jacket to provide cathodic protection, and then the jacket form is pumped with grout. This grout provides concrete repair and provides an activative environment for the anode. So there were several considerations in selecting the specific type of a CP jacket. The DOT required that the jackets extend from just below the cap all the way to 1 to 1/2 foot from the mud line. So the entire pile length had to be encapsulated. And if you remember the photo of the bridge, the pile lengths were very different, and we had piles that were exposed just to marine and tidal zones, as well as piles that were in the submerged, tidal, and atmospheric exposure. So the selected jacket had to be active in all three of those zones and provide protection in both marine environment and atmospheric environment. So VCS selected a mortar-encased, self-activated distributed zinc anode system. You see an example in the photo here. So these rectangles strapped to the pile are the mortar-encased distributed anodes. We selected the distributed encased anodes because they can remain active in the submerged, tidal, and atmospheric zones. We had to use two different types of distributed anodes: marine anodes that are active in wet environments, so submerged and tidal zones, as well as atmospheric anodes that have a higher amount of activator in the encasing mortar and can remain active in the dry atmospheric zones. For the CP design, the jackets were divided into two main categories: structural jackets that had supplemental reinforcement designed by the structural engineer, and then non-structural jackets that only needed cathodic protection. Each group was further subdivided into two categories based on the presence of atmospheric exposure. This slide shows an example of non-structural jacket CP design. The short pile that you see here is a pile that was only exposed to submerged and tidal zones. And these type of piles only used marine anodes. The longer pile was also exposed to atmospheric exposure at the top of the pile. And here we used marine anodes just below the water line, all the way to the mud line, and marine anodes extended up to 2 to 3 feet above the water line. The rest of the pile used atmospheric anodes. You see that there is more anodes at the top of the pile, and this is to compensate for the additional reinforcement at the top. This slide shows a cross-section of the jackets. This is for a structural jacket. So for structural jackets, we ended up adding additional 4 inches to the pile thickness, and for non-structural jackets, it was 3 inches of additional thickness. The DOT also wanted each jacket to be monitored, so a monitoring box was installed on the bend caps above each jacket. Here, we had a shunt to monitor the anode current output and a test connection on the other side. The test connection and the shunt had bolts coming out to the outside of the box, so a technician can take measurements without having to open the cover of the box. The red wires you see connected to the shunt are the anode wires, and the black wires are the structure connections that are connected to the pile reinforcement. The jacket installation started in December of 2021 and is still ongoing. VCS is on site performing measurements on the jackets. And the CP criteria that is applicable in this case is the NACE SP0408 standard, which is cathodic protection of reinforcing steel in buried or submerged concrete structures. So this publication says that in order to achieve cathodic protection, you have to have an instant off potential that is at least negative 850 millivolts or more electronegative, or 100 millivolts of polarization. So all the jackets that have been installed so far have achieved the 100 millivolt polarization criteria. We're also measuring the current at the shunt at each pile, both at activation, that's the initial current, and after 24 hours. The total average current measured at the shunt is so far 248 milliamps. However, because the piles have very different lengths and different number of anodes, this number varies quite a bit. So a better way to compare them or to look at the jacket performance is to calculate the current output per square foot of steel in the pile. And here the initial current is 18.5 milliamps, and after 24 hours the current is just below 9 milliamps. This photo shows the jackets that are being installed. At the bottom, you see the FRP jacket. The darker colored rectangles at the bottom are the marine anodes, and the lighter brown colored ones are the atmospheric anodes. And this is a photo of after the jackets have been installed completely. So in summary, evaluation is key to understanding the health of the structure. You can have cracks in a marine environment that never develop delaminations and spalls, but have severe section loss of the reinforcement. And cathodic protection jackets can effectively address corrosion deterioration of reinforced concrete piles. Distributed anodes can be used to provide cathodic protection in both submerged, tidal, and atmospheric zones. And CP jackets are not just for marine structures. They can be used for bridge columns, for example. So they can be used in atmospheric exposure alone with atmospheric anodes.
Time for one question.
Good morning. Very good presentation. I have a comment and a question. It's something that the comment is that regarding something that Natalia mentioned is that on these pre-stressed piles, by the time you see the outside external visual signs of cracking and all that, there is significant more cross-section loss than on a regular steel pile. And not only that, on hollow core piles, if the crack could have been induced toward the inside, toward the hollow core, rather than the outside, making more complicated the situation how to detect this. But my question is, Natalia, I noticed that you had a very high current density in there, the 18 milliamps per square foot, and normally the designs call for like 2 milliamps per square foot, and that's for the atmospheric part of the cathodic protection system. My question to you, being these pre-stressed piles, pre-stressed steel, have you observed at any point any very high potentials that might suggest overprotection on this?
No, we haven't. So yeah, we're measuring the potentials, and I believe so most potentials are around negative 600 millivolts. So they're not getting to negative 850 even. So no, we haven't. We designed for 2 milliamps per square foot at the end of the service life, which is 20 years. So the current is expected to decrease over time. So we're aiming for 2 milliamps at the end, and that's why you're seeing a much higher current density. Thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.